Welcome to another lecture. So we are still on that counterfort retaining wall problem. So hopefully we will complete the problem with this lecture. So all the design is over except the design of the actual counterfort itself. Okay. So design of toe slab, heel slab, and stem is over, and we had also detailed it. Now we have to complete the design of the counterfort. Now, counterfort, as you know, it's a triangular shaped element, and basically there are three things for which you have to design the counterfort. So, first and foremost, of course, the soil pressure, which will induce a cantilevering effect on the counterfort retaining wall. So, as I said in the earlier lectures, this counterfort retaining wall, it should be designed like a T-beam. So you can imagine this counterfort, it's actually carrying some portions of the top portion of the vertical stem, and the same portion is extended throughout its depth, whereas this portion is increasing in size. So you can imagine this as a T-beam of varying depth. Maximum depth is here and it is varying to zero depth except the flange portion. There is no separate web portion here. It is a rectangular section here. So the counterfort, you can treat it like a T-beam. That is the first and foremost thing. Second thing is, when due to the soil pressure that is incident on the wall, there is a chance for the wall to detach from the counterfort. So this junction should be strengthened. So that strengthening is done by introducing horizontal stirrups between vertical stem and counterfort. So that should be designed for, and also this heel slab is subjected to downward pressure everywhere. So there is a similar chance of the junction between counterfort and heel slab to detach. So we need to provide vertical stirrups as well, so that it can achieve the same purpose as the horizontal stirrups connecting vertical stem and counterfort. So those are the three things we have to design the counterfort retaining wall. Now ideally I should have shown a cut section here to show you how the T-beam will look like, but I guess all of you are able to imagine it. Okay. So let us proceed for the design. So first let us design the T-beam. Now this is the section passing through the counterfort. So this is the vertical stem, and let us assume this angle is theta. So from trigonometry you can easily calculate the angle theta. Okay, before that let us calculate the forces required for the design of the T-beam. Now the soil pressure is varying with depth, right? It is 0 at the top and maximum at the bottom. Similarly, the counterfort which is to be designed as a T-beam is also varying in depth as it goes towards height. So let us divide the design into three parts, one at base and then middle third and upper third. Okay, so at base this is the active earth pressure at the bottom. Now using this, so this is a triangular distribution, right? So using this you can calculate factored bending moment and factored shear force that will be incident on the counterfort wall. Now here the difference is, see, when we are designing the regular retaining wall, we will consider the length as unity. Okay, so when you are designing for the counterfort as a T-beam, you cannot consider length as unity because the counterforts are spaced at a certain spacing. So the clear spacing is 3 meter, thickness of counterfort is 0.5 meter. So center to center distance between counterforts is 3.5 meter. So that difference will be there here. You can't consider unit length, you have to consider the length or the center to center spacing between counterforts. So using a factor safety of 1.5, you can calculate factored bending moment, factored shear force. and from geometry, as we said, theta you can calculate. So its size at the lowermost portion is, you drop a perpendicular to the inclined line. So the depth you calculate here, that is the depth of the T-beam at its base. So you can, using geometry, you can easily calculate this as well, dl cos theta. So this is the depth of the T-beam at the base. So you can imagine it as a very deep T-beam. Just try to imagine a T-beam of depth 2.287 meter. So probably might be the deepest T-beam you will ever see or design. Okay, so this is the total depth. Now let us calculate effective depth. Assume clear cover of 50 mm, bar die of 25 because we anticipate huge loads. So this will be the effective depth. Now T-beam design is peculiar, so I'm not sure. I hope you might have studied in DCS 1. So for T-beam, see, this is the clause that deals with T-beam in IS 456 23.1. So there is a formula for calculating effective width. Okay, so L0 by 6 BW plus 6 times DF. So using this formula, we can calculate the effective depth of the T-beam at the base. So span is 8.5 meter, which is the length of the total span of the cantilevering T-beam. BW is the width of the web. So the thickness of the counterfort is 0.5 meters, so that is that. And plus you will have 6 times depth of flange. So here depth of flange is nothing but the depth of the top portion of heel. Actually it's not top portion because we are dealing with base. So we have seen that in this counterfort it is tapering from 300 to 600 at the bottom, right? So it is 600, depth of flange is 600 for the T-beam at the base. So this is the formula for BF as per IS 456. Now this formula we got some numbers. So the code says that number should not be greater than breadth of the web plus half the sum of clear distances. So that we can check. So it is clearly more than the width of web and clear span, which is 3.5 meter. So you have to adopt a width of flange of 3.5 meter. Again, huge dimension, right? So let us now with the dimensions fixed. So you have the effective depth ready, you have the width of flange ready. Again, I regret not drawing the plan view of the T-beam here, but I hope you are all able to visualize the T-beam, right? Okay. So for T-beam, to carry out the design, first what we'll do is we'll arrive at the approximate quantity of tension steel. So this is an approach of designing T-beam. So what we'll do is, see, first of all, in the classical design approach of beam, so imagine this is like a beam, right? So for design of beam, you need to know the lever arm, especially for a section like this, which is complicated, means it's a T section, right? So lever arm, approximately you can calculate it as a larger of 0.9 times depth, effective depth, or D minus df by 2. So we can calculate both. So maximum comes out to be 2001 mm. Okay. So once you get the lever arm, you can calculate AST required. So AST is nothing but you can use this expression, moment equal to force into lever arm, right? So this is the moment, this is lever arm. Now force is 0.87 Fi, that's the allowable stress in steel as per limit state design, and this is AST. So AST into 0.87 Fi is the force. So using this relationship you can calculate AST required, which turns out to be 39.66 mm square. So we had assumed a 25 dia bar here. So number of bars required you can calculate, which turns out to be 8 bars. Okay. So what we'll do is, so remember this 8 bars has to be provided on this edge, because see soil is applying a force along this direction. So this edge, which is the inclined face, will be subjected to tension. So that 8 25 dia bar has to be provided along the inclined face. So that is here what I shown. So you have got 8 bars. So let us assume that you are providing it in 2 layers. So remember its width is 50 mm. Sorry, 50 centimeter. This width of the counterfort is 50 centimeter. So if you are providing the 8 bars as 2 layers, you have 4 bar, 4 bar, and assuming a clear spacing of 25 mm between both layers, what we can do is, using this configuration we can calculate the actual effective depth. Now okay, so now what we'll see, what we have done here is, whatever we calculated here, this is only approximate steel. Okay, because we have used this approximation. Now based on the starting point, we will verify whether the steel calculated is okay or not. So that's why once the bar is fixed, we are again working out the effective depth based on the actual configuration, so that we can calculate the actual ASD. So if you assume 2 layers of 25 dia bar with a clear gap of 25 mm, effective depth is 2287, which is the actual depth here, right, minus 50 clear cover, then 25 dia bar is there, one layer, and the centroid of this bar group is at the center. So 25 is the spacing between the bars, so 25 by 2 is the center, right? So this is the new effective depth. So using this effective depth, let us assume, let us make an assumption that the neutral axis is located within the flange. Okay, so this is the flange, right? This is the a vertical stem, this is the counterfort wall portion itself. So let us assume that the neutral axis is within the flange portion. Okay, so we have to verify the assumption. How to verify the assumption? So sorry, we are assuming that neutral axis is located at the interface between flange and web. Okay, so to verify the assumption, we will calculate moment of resistance. So moment of resistance, you know this formula, right? In IS 456, you might have either in this form or a different form, I'm sure you might have seen it in BCS 1. So it is page number 69, sorry. Sorry. Yes. So you might have seen this, right? For a concrete portion, its effective force is this much. Lever, the centroid is at a distance of a 0.416 XU. So using that formula, I'll calculate moment of resistance. Okay, 0.362, which is nothing but more exact value of this 0.362 FCK XU. So XU here I am taking it as this depth. I am assuming that neutral axis is at the interface of web and flange. So you calculate the moment of resistance, and the moment of resistance actually comes out to be more than the actual moment. So remember, this is the actual the moment of resistance comes out to be greater than the moment that you have calculated. Okay, so which means the neutral axis lies within the web. Okay, so it means our problem is simplified. So now you can calculate R mu by BD square. So PT by 100 you can calculate, well known formula using which you can calculate AST. So this AST calculated now with the actual approach is closer to the initial approximate value we had arrived at. So the design is fine. So which means 8 number of 25 dia bars are sufficient. Okay, so that is AST. Now we can also verify that with AST minimum. So remember, this is a beam, we are designing it as a beam, so you have to use the clause corresponding to minimum reinforcement of beam 26.5.1.1. Sorry, I should have written the page number, but anyway it is somewhere. Yes, so this formula, using this formula, so in this formula B is the breadth of the web. Okay, so you take B appropriately. So AST minimum you can calculate, which is which if you calculate it is lesser than the actual AST, which means okay, you don't have to increase the AST. Okay, so that will be the design of the T-beam at the base. Okay, remember we divided the T-beam design into 1/3, 1/3 and 1/3. Now going to the above 1/3, what we will do is, now remember, see, this is the height, right? The total clear height is 8.5 meter. So you go 2/3 of that, so height is 5.666. So based on that you calculate the reduced active pressure, factored bending moment, factored shear force. Again, don't forget to include the depth, because now you have to consider the spacing of the counterforts, right? You are not designing it for unit length. So we repeat the same procedure that we did for the base, right? So it's a complicated procedure, I know, but some of these things hopefully it should have been covered in DCS1, I believe, in when you design the T-beam. But anyway, the procedure is similar. So you follow the same procedure and we'll arrive at AST. We'll find that you require 4 number of 25 dia bars. So remember, at the base when we calculated we had arrived at 8 number of 25 dia bars, and at middle third we are getting 4 number of 25 dia bars. So remember, at the base this was our configuration. So what we will do is, out of these 8 bars, which is divided into 2 layers, this 1 layer bars we will curtail or stop at 1/3 height, and only this layer we will continue it throughout the height, because for the middle third we are getting exactly 4 25 dia bars. So that is exactly what we will do. So that is the design of the counterfort walls as T-beam. Now remember, I told you there are 2 more things. Counterfort wall has to be designed to ensure that the interface between vertical stem and counterfort is strong, and as well as interface between heel slab and counterfort is strong. Okay, so for which we require to provide stirrups. So let us first look at the interface between vertical stem and counterfort. So what's happening is, between vertical stem and counterfort you will have shear force. So we had calculated the shear force, right? Initially we had calculated shear force. Now T-beam, this is a T-beam which of varying depth. So when the depth is varying, you have a special formula to calculate shear stress, because the effect of bending also will come into the shear force. So it is given by clause 40.1.1. I am not sure if you have used this clause before. So if not, you can go through it. So 40.1.1. Yes, yeah, this is the formula. So this is the formula. Here there is a plus or minus. So it is minus if bending moment is increasing along the same direction as the increasing depth of the beam. That point you can read here. Anyway, so in expectation that you might have seen this formula, even if you have not seen, you can go to clause number 40.1.1 and you can read more about this formula. So using that formula, you can calculate shear stress, right? Now, PT you already know. At the base, you are providing 8 number of 25 diabar. So using PT, just like our normal procedure for shear force, you can calculate the shear capacity that is already existing. So based on PT, you can calculate the shear capacity that is already existing for M25 grade concrete. For the balance shear force, you will design the stirrups and you will find out the spacing. So let us assume 25 let us assume 2-legged 10 dia stirrups. So with that assumption, using this formula which I just mentioned, which I used many times, we can calculate the spacing. So spacing comes out to be 886 mm, which is very large, which means we have to apply the clause for maximum spacing. We have to check against it, which is 26.5.1.5. I have written it here so that you can reference this. 26. Okay, anyway, with this you might have seen this. Okay, let us go to that. That's better. 26.5.1.5. See this. Yes, it is this particular clause. So maximum spacing cannot exceed 0.7 times effective depth or 300 mm. So you check against that. So clearly it is exceeding that. So the spacing you have to provide is 300 mm. So this stirrup design is as per the normal shear consideration, but we said that there is a possibility of this interface to detach. So why is that? Because the pressure, bulk of the pressure is acting on the vertical stem. Okay, so it will try to, soil will try to apply the force in this direction. As a result of this interface as a possibility of cracking. So you have to design the ties for the interface. So whatever we discuss in this step, it is the stirrup design as per normal shear. Now you have to check for the stirrup spacing for the tension between the interface of both vertical stem and counterfort. So tension you can easily calculate it. See, this is the soil pressure at the base. We had calculated it earlier. This is the soil pressure at the base. So using that soil pressure, you can calculate. Now you multiply that by the width to get the total force that is acting at the base. So remember, we are considering the base right now. So this is the total tension that is acting, that is trying to detach the interface between counterfort and stem. So the vertical horizontal stirrups should take this much force. So apply a factor of safety of 1.5 and into this tension divided by allowable stress in steel. So 415 grade, it means in limit state design is 0.87 times 415. So this much area of steel or stirrups should take the tension. So again, let us proceed with the same assumption of two-legged 10 dia bars. So if you proceed with the same assumption of two-legged 10 dia bars or 10 dia stirrups, sorry, you can calculate the spacing. So the spacing you are getting to take the tension between vertical stem and counterfort is 238 mm, which is lesser than the spacing requirement of normal stirrups. Okay, so shear demand is greater for the tension requirements which will prevent the detachment. So you round it off to 200. So provide horizontal stirrups or ties or stirrups, because it's a beam, so you have to call it stirrups. 2-legged 10-dia stirrup set, 200 mm center to center. So this is the stirrup, horizontal stirrup connecting the vertical stem and counterfort. Similarly, you need to provide vertical stirrups connecting heel slab and counterfort, so that it will prevent detachment of this interface, because remember, heel slab is subjected to downward pressure, right? So that downward pressure we had calculated it earlier. So let us design that vertical stirrup now. Okay, yeah, this is for middle above 1/3. That will skip. That is, you can just read it. It is easy to understand. Now for vertical ties, what we'll do is we'll go back to see. In the earlier lecture, we had seen this, right? So in the design, we had designed for the heel slab end last 1 meter, right? When we designed for the heel slab. So here we have already calculated the soil pressure. So you can take average of the soil pressure, and for the average of the soil pressure, you can make it factored and divide it by allowable stress in steel. Again, assuming 2-legged 10-dia bars, you will get the spacing. So the spacing works out to be 100 mm. So that is the spacing that you require at the tip, because we have calculated the tip. So as you move inside the heel slab, this pressure reduces, right? So the spacing can be increased. So whatever you calculated here, you provide for 100 mm for initial 1 meter. After that, beyond that, you provide at a spacing of 150 mm. Okay, so that is the design of counterfort wall. Now let me detail it. So I detailed the plan and the section in both in one page. So remember, detailing of other parts we had already taken them up. So I won't be discussing those. So this includes that part which we have already discussed. So if you look at plan view, at the base you have 8 25-dia bars as 2 layers, and then you have this you have horizontal stirrups and vertical stirrups. So this is the horizontal stirrup, and vertical stirrups will be seen as a dot. So vertical stirrup, we had said that spacing is 100 meter, initial first 1 meter, sorry, spacing is 100 mm, initial 1 meter. Beyond that you can reduce it to 150 mm. So that is what I mentioned here. And for the horizontal stirrups, we had worked out the spacing and dia here, so that is what we'll employ here. So we had seen that you need to provide 2-legged 200 mm center to center. So that is, yeah, 2-legged 8-dia. So actually it's 10-dia 200 center to center. Now in the upper 1/3 and all, I not gone through the calculation detail. We can provide 8-dia. So that's why I written a bar here, 2-legged 8-dia or 10-dia, depending upon where you are looking at 200 mm center to center. So this is the section. You have 8-dia, 8 25 number bars going up. So beyond a point, only 4 25-dia bars need to go. So this is the curtailment point for 4 bars. And this is the vertical and horizontal stirrups which we discussed. So it is a long lecture. I think it's only became very lengthy, but so go through it. Since it is a new topic for you, some of these things might be new for you, but it is simple mechanics, in the sense that if you think about it, it's not difficult to understand. Okay, so if you have any doubts, please let me know. Since it was a long video, I couldn't discuss every nook and detail of it in, with perfection. But I'm anyway sharing these notes with you, and I hope you will be able to follow it. So this completes the long counterfort retaining wall problem. So please go through it and let me know if you have any questions. So in the next lecture, I will be taking up basement walls, which is also yet another topic mentioned in your syllabus. Okay. So if you have anything, please let me know. Thank you.